this video we're going to discuss Introduction to Mathematical Proofs Part 2. So let's start. The previous video we discussed direct proof and proof by contraposition. So we're going to continue today with vacuous proof and trivial proof by contradiction, and perhaps just those two methods. So let's start off with a vacuous proof. A vacuous proof shows that if you are able to show that P is false because P implying Q must be true when P is false. So the idea here goes back with the truth table of the implication. So you have PQ, for example, and say this is false. So the implication, if we recall, it's giving us truth if it is false implying false, truth when it's false implying false. So as we can see clearly, when the P or the antecedent, the hypothesis, is false, then your implication is automatically true. So hence the NAT of P directly implies the truth of your implication. So that's the vacuous proof. For the trivial proof, however, so we have a similar scenario where if you are able to show that Q is true, it follows that the implication P implying Q must also be true. And why is that? If you're going to check the truth table again, so if you have an input which is a Q which is true, this one, so Q which is true, and another Q which is true, we are assured of the output to be true. Because after all, the implication is just false when the first statement, the antecedent, is true, implying false. So this is the only case where it is false. So therefore, this particular case, we will call this basically the trivial proof. Show that Q is true and the implication is automatically true. Let's check some examples. Proof that the statement, if there are 30 students enrolled in this course this semester, then 6 squared is equals to 36. The first statement is unclear. What class is this? So somewhat we go directly to the second statement, which is mathematically true. You have 6 squared is equals to 36. And again, we know that the Q, the consequent, is already true. And from the previous definition, the implication will be automatically true by trivial proof. In the next example, we have, say, prove that the statement, if 6 is a prime number, then 6 squared is equals to 30. So these statements are both mathematical, but is 6 a prime number? So we know that this is already false. 6 is not a prime number. So no matter what's the consequent, whether this is true, whether this is false, automatically by vacuous proof, since the first statement is already false, by vacuous proof, false implying Q, or the consequent, is automatically true. So this is by vacuous proof. Next, we proceed with proof by contradiction. So for proof by contradiction, we're going to assume the NAT of the premise is true, leading to a contradiction. So we must first clarify what is the NAT of P. So the P here is not the antecedent. The P here is equals to the whole premise. So this will come in important later on. So it's important that do not equate the NAT of P here to the implication P implying Q. Again, this is basically not the antecedent. It is the whole premise. So if the premise is an implication, you're going to negate the whole implication. So for example, prove that square root of 2 is irrational by giving a proof by contradiction. So the whole premise here is this one. So square root of 2 is irrational. So as you notice, this is no longer an implication. So this is just a statement that square root of 2 is irrational, because proof by contradiction is, after all, not dependent on implication. Unlike the previous ones that you have direct and proof by contraposition, which is very much patterned with respect to an implication. So if you are going to solve this problem, first let's identify the assumption. So first, you're going to assume basically the negation of your premise, and we assume it to be true. Second step, basically we are going to somewhat show a contradiction. So basically a contradiction is a statement that is always false. So if you have, for example, odd is equals to even, that is always false. Say for example 1 equals 0, so that is always false. That is a contradiction. So assume that the NAT of premise is true, so that means we're going to negate our premise. So if our premise, which is say square root of 2, is irrational, so the negation of that will be square root of 2 is rational. And we have to assume it to be true. Now, using this assumption, we're going to somewhat show that there is a contradiction somehow. So, for example, what is a rational number? So, we know that a rational number is basically a number that you can express as a ratio between two integers. So a, b integers, and b is not 0. And important component of the definition, which we're going to somewhat utilize here, is a and b have no common factors, no common factors other than 1. So, for example, 3/5. So, 3 and 5 has no common factors other than 1. So, in other words, a and b is in simplest form. So, let's start with the assumption now. Square root of 2 is equals to a over b. So, this is already assumed to be true. We're going to manipulate this by algebra. So, square. So, we'll have 2 equals a squared over b squared. So, if we cross multiply this, we have twice of b squared is equals to a squared. And from this statement, because a squared is twice of a certain number, say if we let this b to be k, for example, so this a squared is twice of k, therefore I can conclude that a squared is even. And there is a theorem that if a squared is even, then a is also even. So if a is even now, therefore we could express a, say, as twice of m, for example, where m is an integer. Now, if we use this relationship, we have a equals even. If we substitute it back to the first statement, so we have, for example, we have 2 is equals to, say, 2m squared over b squared. So we end up with twice of b squared is equals to, say, 4m squared. So from this, we could factor out the 2 from 4. So we could reduce this to, say, 2b, or let's just cancel the 2 in this case. So b squared is equals to twice of m squared. And how is this significant? We know now that b squared is also even, because if we let m squared to be any number, maybe x for example, so this will end up to be twice of x. So b squared is also even. So recall that we found out earlier that a is even. So if b squared is even, therefore b is also even. And that will be the foundation of a contradiction, because if we have a over b, then even over even is not in its simplest terms. So it violates this definition that there are no common factors other than 1. So for the next meeting, we have to an exercise, so give a proof by contradiction of the following theorem. If 3n plus 2 is odd, then n is also odd. That's it.